Very good morning to everyone. In our product development, automotive issue development journey, we are going to reach the next milestone. In that, we want to implement serial communication interface in our product. Actually, why we need communication interface in real time? Because when it is the serial communication interface is something like a communication channel or a bus system through which you can interact with your microcontroller from the external world. That means from PC, from another computer, or another microcontroller, you can interact. You interact with your so the bus system, whatever the bus system, network bus system that we have today, no, for them, this is the mother of all bus system is serial communication. That is serial communication interface is mother of all bus communication system. Right now, the another name for serial communication interface is an RS-232 communication, and then UART communication. Like that, we have different names. The primary purpose is when the people now what I am doing is when I want to flash a microcontroller program to my microcontroller, I have to remove the microcontroller from the motherboard, and then I have to connect that to the flasher. Then I will program it using another software. So this is like a time consuming. Sometime I may break the microcontroller pins when I remove or connect in those times. Sometime we have this one discharge. So because of that, your microcontroller board or your controller will burn some time. So otherwise, it can be corrupted. So to avoid those things, what the people have developed is like they have developed something called as some concept called as a bootloader, so that they only one time they will flash a software, a microcontroller program inside the microcontroller using the method that I am using now. They will connect it to the flasher and then flash it. Once they successful in that bootloader flashing, then they can simply use some Teraterm or other serial communication bus system to flash their code. That means they no need to remove the chip from the motherboard every time. The bootloader program will have the serial communication interface implemented in that. This is very basic I am talking about. Nowadays, we have a CAN flashing. If they implemented a CAN in that product, and you have a necessary interface to connect with the PC for CAN, then they can do CAN flashing as well. The CAN is very advanced. We don't need to go there now. So this is very simple, and it was there for a long time. It is used by the that is a motherboard manufacturer for a long time. Right now, it is just like to bring the external code that you are writing in your PC. That means an X file to the microcontroller memory. We can do it in a different way. We can connect the flasher. We can remove the microcontroller from the motherboard and connect it to the flasher and do the flashing. But it is time consuming. As I told, there are a lot of practical issues. So to avoid that, they made this concept. So our aim is we also want to make a bootloader, serial uh, communication bootloader in our microcontroller. That means in our product. Then later we will use this serial communication to flash our executable to the microcontroller. So that is very easy when the code become very big. So in that time, we should not every time remove the microcontroller from the motherboard and do all these stuffs. So that is the aim. Not only that, this is one primary primary purpose that we want to implement serial communication interface in our product. The next one is when you want to communicate some information from your microcontroller to the external world. Right now, otherwise your embedded product to the external world, there should be some mechanism. Anyhow, as we are developing a CAN product, we can do that via CAN. Right. But there are certain configuration related things, or to do them, we need some sort of bus system which is other than CAN. For that, we can go for again SCI, and then when you want to interface some sort of sensor which is having a communication bus system, in that time also the SCI will be very much helpful. So in total, it is a very key thing when you want to develop a product, embedded product using a microcontroller. So implementing the serial communication is very much important right now. So now we are going to do that. But when you look into the subtitle that I have, I said using PIC16F877A. Previously, when I explain this initial design, I used a different microcontroller, no, 16F887. I had an issue with that one. So after doing 2 sessions, I didn't do microcontroller video session. The reason behind that is I faced a challenge with this controller. Sometimes when I try to flash it, the code is flashed, but the behavior is different. It was malfunction sometime. I don't know. It is a problem with my motherboard that I have, or the controller. I am unable. I am not very well versed in using this controller. Because of that, my blinking program worked fine. Then I moved to interrupt. That worked fine. After that, when I go to serial communication interface, I face a challenge. So at this point, I have to make a right decision, because I know I am very well versed in this controller PIC16F877A. So I want to revisit. I want to, because I already did serial communication interface program for a robot arm control for my MTech degree. So I want to revisit the same controller. I want to use it in my product, because this controller also support SCI, so that SPI, so that I can interface CAN controller with this one as well. So there is no issue in that one. That's why I changed the microcontroller now. That is the change in the project that I have listed here. The microcontroller that we initially decided to use for automotive is changed to PIC16F877A. So this is another PIC controller with the same family, but it has its own features. Okay, now. So after that, how to implement this? I told that we have to implement serial communication interface. We cannot implement that just like that. We have to do a lot of how to do that one. I believe I have given the enough explanation about SCI. SCI is a serial communication standard. Using that, you can exchange one character at a time. That means a packet size can in a single packet, you can carry 1 byte right now. In CAN, we are carrying 8 byte in a packet now. So here it is only 1 byte. That is the difference. It also an asynchronous communication standard, and it is also having the handshaking bits like start of frame, end of frames, and those things. So it is similar to CAN, but it is a somehow lowest standard. It is there for a long time. That if you understand that about SCI, that's enough. Then why we need that in our product? That is also I explained right now. So why we need that? Because we want to transfer the external code to a microcontroller from the PC, so that we want to implement a bootloader for that. When you want to implement bootloader, we require this one. Any one bus system can be used, but in our we are choosing SCI right now. That is the aim. How to implement that? How to implement that? We should have the microcontroller that we choose now, that should support serial communication interface. So luckily, PIC16F877A is supporting SCI. So it has a peripheral for that. So only thing that we have to do is we have to configure that peripheral, and then we have to use it right now. That we are going to do today. So we are going to do that, and we have a problem statement in next slide. We are going to do that. The problem statement is implement necessary microcontroller program to transmit character A from the microcontroller to PC every 1 second, and demonstrate that transmitted character is received successfully in PC using Teraterm. The problem statement is we have to write a microcontroller program which is going to transmit character A using SCI. using serial communication interface, it is going to transmit character A from the microcontroller. Then when it is transmitting, somebody should receive. Right now, for that, there is a open source program available in the internet called Terraterm. This program, if you configure your baud rate and this can receive the character, the bytes via SCI and can display that in your PC. So it is something similar to hyperterminal that we had in Windows XP. So as Windows discontinued to come with the hyperterminal in modern OS like Windows 10 and Windows 11. So this is another open source program that is available in the internet. You can take it and use it. The Terraterm, no, so it can display the transmitted character from the PC after successful reception. But there should be a link, wired link between your microcontroller and your PC or laptop. So in my case, I bought a motherboard. No, in that motherboard, they have a serial port and they already implemented the necessary circuitry so that they even have a port in that. I can connect my RS-232 cable or a serial SCI cable to that port, and then I can connect there is something called as RS-232 to USB converter. I can connect that one to the PC. Then I can open Terraterm and make the necessary configuration. After doing it, I can easily receive character from the microcontroller. So I believe most of you knew this one, those who work with microcontroller. If you don't work with that one, this is the introduction. So the Terraterm is an open source program. It supports serial communication interface. So using that, if somebody is transmitting, other one should receive now. So for receive, in our case, the receiver is our laptop. So for this Terraterm will receive the packet from serial port and decode it and will display what is received. So to make this communication to work, we need a physical link between microcontroller and laptop that is achieved via RS-232 port in my motherboard and then RS-232 USB converter. Why we are using RS-232 USB converter? The reason behind that is modern laptop doesn't have COM ports, so that we use this option right now. So that's all about the hardware detail. Then let us jump to the programming now. Here is my program that I have written. See, now the microcontroller is changed. Here are the necessary configurations that we have to do. So first I selected the F oscillator and HS and the remaining settings are off. Then I configure the external frequency as 20 megahertz. This is one of the important thing that we have to do. Then I have written an interrupt service routine right now. So before visiting this interrupt service routine, let us jump to my main function and then we'll come back here. The moment we come to the main function, we assign a register called T1 controller, T1 con to the value 1. What does that mean? So the T1 con, when we assign the T1 con to 1, which has a meaning, actually we enable or we start the timer 1. Timer 1 in the microcontroller. This microcontroller has 3 timers, I believe, timer 0, timer 1 and timer 2. So this timer 1 will be started. So there is a bitmap for this register, T1 control register. It is a register in that microcontroller. We are giving the value 1 to that one. Let me show you the bitmap. So here we have So the prescaling, I'm not assigning any prescale, and then so here we have assign only one only, no. So the first two, these bit 7 and 6 are that is read as 0. That means they don't care. Then we have a pre-scaling. We don't do any pre-scaling. And then timer 1, oscillator enable control bit, that we are setting it to 0. And bit 2 also set to 0. This one. And timer 1, clock source select base. That means timer 1 going to use which clock source. So this microcontroller can accept the clock input from external circuitry as well. If you want to use the clock supplied to the microcontroller, that means the crystal oscillator that we connected, no, the 20 megahertz crystal oscillator. If you want to use that clock, you have to set this bit to 0. That is what we are setting that value to 0. Then finally, we turn on the timer. We enable the timer. Right now, that we are doing. That is the first step that we are doing. I enable the timer 1. And then timer counter values are set to FF. That means there is a counter value. When you are using it as a timer, so they will start from 0. If I have some other value here, for example, 20 or 30, something like that, from there they will count. So to avoid that, we are assigning the FF to that, so that immediately one overflow will happen. The moment they count it, the timer 1 will become 0. So that is the timer counter value will become 0. They will count from there. So how long they used to count? This is timer 1. No, it is a 16. It has 16-bit counter. That's why they divided into 2 bytes. So from 0 to 65,565, up to that they can go. So only then there will be a overflow. All right. Now after that, in this microcontroller, we have a in the port C, we have pin 6 and pin 7. Those two pins are allocated for serial communication. That you can see it in the diagram, like pin diagram of this controller. Maybe it should be in the beginning. Hmm. 16 of 8, 7, 7, yeah, no, yeah. So here RC6 is a TX pin and RC7 is RX pin. So it is the reception, this is transmission. When we do output, we used to assign the TRISC value to 0. Right now, when we configure certain pin as an output, we assign TRISC bit value to 0 to that one. Right. When we want to consider something as an input, we will set that to 1. This is common understanding that we have for PIC controller. That's why I configure pins port C pin 6 as an output pin and port C pin 7 as an input pin. Pin via pin 6 I am going to transmit, pin 7 I am going to receive. That is the concept. After that, I reset the TRISD value to 0. That means I am configuring the port D value to 0. I think this is not needed. The reason behind that is as I leverage this code from that toggling, the LED toggling, I bought this one. Even if we don't have this, the code will work. Actually, that is not necessary. Then I disable all interrupt because I'm going to do some configuration. While doing configuration, it is not good to have interrupts. That's why we disable all interrupts initially by assigning interrupt controller register to 0. So it is also having a bitmap that I will show when we need to show. Then SP serial port baud rate generation register. For that, we have to configure a value. This value we have assigned to 81x. How we got 81x? There is a formula again. To calculate baud rate, you have to follow a formula. Based on that only you can get it. So for that, SPBRJ. So actually I am configuring 9600 baud rate. For that, 81, I have to load that with 81. See, sync baud rate I. When I have this, baud rate equivalent to FOSC 16 into X plus 1. This is the thing now. So this is the formula. Baud rate equivalent to Let me bring an Excel sheet so that we can do the calculation very easily. Okay. First, our clock frequency is what? 20K, 20 megahertz, sorry, 20 megahertz, 20 followed by 60, 1, 2, 3, 4, 5, 6. So this is our clock frequency. And then desired baud rate that we want is 9600. Right now. Now, what value that we have to load it to the SP baud rate serial port, baud rate generation register. That for that they have a formula here, no? So it is FOSC divided by 16 into x plus 1, right? So our aim is find out the value x to for the 9600 watt rate. So that what I'm doing, I'm whatever that we have in a multiplication, no, when we go, sorry, division, that will that is the x plus 1 is in the division, right? That will go to multiplication when we send that to left side. Again, the baud rate which is in the in this state, no, that will come to the division. So how it will become? FOSC x plus 1 is equivalent to FOSC divided by 16 into 9600, right now. So 9600 minus 1 because x plus 1. So I believe I understand you got what I am trying to say. X plus 1 is equal to this frequency divided by 16 into 9600, 16 to this one, right? X plus 1, right? So how I am getting it? I send this x plus 1 to left side and baud rate to right side. So FOSC divided by 16 into 9600. That is what I am getting here. After that, this is x plus 1. For x, it is this minus 1, right now. So we have to convert that into hex decimal because it is in decimal. That is what? 81. This 81 only we are loading here. I believe you understood now how we come to this value 81, right? After doing this, I am clearing there is a TX status register. That means TX status register means that is only that register only will control your transmission, right? So initially I set that value to 0. In that CX STA, we have a bit called baud rate high that is needed. We have to set that one. Then only we will come into this formula, no? For that, so let me show the bitmap for that register. Yeah. So this one, this means clock source select mode. So it has these bits like clock source select bit and then a 9-bit transmission enabler for whether it is a synchronous or asynchronous. For asynchronous, this bit should be 0. If you want to enable the transmission, you have to set this bit to 1. Then only it will become transmit enable. Then baud rate high also we have to set. Then only we will come to that formula. And then TRMT. TRMT is a read-only bit. It will tell that if the transmission, no, it will happen in bit shifting. So when all your the bits to be transmitted is shifted out to the bus, this bit will be set to 1, right? So it is a read-only bit. So initially when we want to assign to that one, we no need to assign anything. It is a read-only bit. So if it is empty, the transmit shift register is empty so that you can move and move a byte to transmit. By checking this one, you can do that. Then there is a TX9D. TX9D mean I think it is a ninth bit of transmit data. So in a packet, we have only 8 bit can be transmitted, but the 9th bit will be here. Right now, this can be a parity bit also. So after doing that, I set this line make my communication an asynchronous communication. This one said the high baud rate. After that, I also clear receive status register. I can also initialize the reception now, but in this program, I am only going to handle the transmission part. I am not handling the reception part. So anyhow, I just initialize that receive status register to 0. Then in that also I enable serial port, communication, and then I enable receive interrupt, because when a character is received, when a packet is received, there will be a bit RCIF. That bit will be set. So to notify that the reception happened. So for that, I enable the interrupt here. Similar way, when I transmit, when I do a successful transmission, there will be interrupt, right? So that is also enabled. TX transmission interrupt enabled. Then continuous receive also I enabled. These are something related to reception, but anyhow, we are doing it. And then I enable the global interrupt, peripheral interrupt, and then transmit interrupt. Also, finally, I enable the transmission. So these are the different bits, the bits that we have to set in order to enable serial communication. Once we complete all these settings, I call this enable interrupt function. This only will make the all interrupt to work. After that, I just go and wait in an infinite loop. When I am waiting, because I also started the timer right now, this timer will overflow. When it is overflowing, we will get a timer interrupt. For that only we have written here interrupt service routine. So in this interrupt service routine, when the timer is timer 1 is expired, or it is, or there is a overflow in that one, that program control will come here. Here I am checking whether the timer 1 interrupt flag is set, because this flag will be set if the timer there is a overflow. If it is setting, I maintain a counter. This is a little bit strange, you know. Okay, timer overflow happened. After that, why we are checking the counter to 76? That is having the we are doing it for another reason. The reason behind that is the timer one time, if the timer 1 is, if there is a overflow in that one, how many times the overflow should happen in order to achieve 1 second delay? That is also be calculated, no? How to calculate that one? So for that only we use this count is equal to 76. Let me explain you how we are come to this 76 first of all. For that, we have to do a calculation. First thing is our clock frequency. Then when you use a timer in a certain mode, when we use the internal clock of the microcontroller, your timer frequency will be, timer input frequency will be what? This divided by 4. That means 5 megahertz only. So then we have to find out the tick. The tick is, if you set, there is something called as a prescale. This prescale means further you can divide the clock. If I set that value to 1, my tick, that means 1, when a timer count a 1 tick, that means 1 tick, what is the time it will take to make a single count, 1 count up? If the timer is counting from 0 to count 1, how much time it used to take? That you can count find out using 1 by timer frequency, because we don't have prescale, no free scale is there, right? Because we set the prescale as 1. So after this is the tick value. So in order to make the overflow, how many ticks are required? Because there should be an overflow, no? So overflow will happen only when your timer counter reaches FFFF 65,535, I believe. To reach that one, so time tick for overflow. Otherwise, time at the overflow. Time for overflow. Time for overflow is this multiplied by 65,535, which is nothing but FF, almost 13 milliseconds. So when you have 13 milliseconds, our aim is 1 second, every 1 second we want to transmit, no? So if you put this to 1 by, you will get 76. Right now, when I make 76 time, when timer 1 is overflowing 76 time, then I will get 1 second delay. That is why we are using 76 here. Right now, when the timer is overflow, when there is a overflow in timer 1, we check whether the count is reached to 76. If it is not reaching to 76, we simply increment the counter. That means we are accumulating the time. The moment we reach 76, that means moment we become 1 second, in that time I move 65, the decimal equivalent of A. Because for A, capital A, ASCII value is 65. I just move 65 to TX register, transmission register. When I put that one, after I do that one, I make the count to 0, because next time after 1 second, I need another A to be transmitted. For that, the count should increment, no? Because we already reached the 76. So that I reset the count value to 0. After doing this stuff, either I increment the count or I put 65 to TX register. I just clear my timer counter to 0. This is a safer side of thing that you can do. After that, I also clear this flag, because this flag should be cleared in software. It will not automatically, it will not clear. If you don't clear it, next interrupt will not happen right now. So we have to clear that one also. So we are doing it when there is a overflow in timer 1 and the interrupt service, there is a interrupt, timer interrupt happened, and the program control is transferred here. This is when there is a timer overflow. After that, when I put this to TX register, no, what will happen? The microcontroller will try to shift it to outside world. At one point of time, that shift register, no, that will become empty. When it become empty, in that time, transmit interrupt will happen. That means the transmission is over. You can transmit the next thing right now. So in that time also, they will come to the same interrupt service routine. This time, there is no timer overflow, right? So they will come here then. So there is a transmitter shift register empty. So we check if there is a successful transmission and the shift register is empty, these 2 bits will be 1. If they both are 1, the transmission is successful. Then what I do, I just clear transmit interrupt flag to 0, so that I can allow to next transmit interrupt to happen. If you don't clear this bit to 0, if it remains in 1, so you will not get a next transmission interrupt, so that you cannot transmit the next character right now. That's all. This is the program. So this program will, if I flash this program to my microcontroller, it will keep on transmit character A every 1 second from my microcontroller to Teratom. Right now, let me check that whether that is doing it. I already flashed this code in my, I written this code and I flashed that in the microcontroller. Let me demonstrate how that works. So for that, I have to bring Teraton. See, I am getting A. Every 1 second, I will get A now. Right. So while I am getting A, what I am doing, I simply turn off my microcontroller board. I think as I stop the microcontroller board, that means power to microcontroller board, the transmission is stopped. So now again I give power to that. So when I give power back to that, again it is executing the program and it is transmitting character A. So this is another new achievement that we got. So in our new milestone that we reached in our product development journey. So with this, I want to end today's session. I will catch you with more detail in upcoming session. Right now, thank you. Thank you for your patience.